Hello guys, welcome back. Okay, today we got a hard problem from Leetcode. That is, count the number of arrays with k margins adjacent. Okay, adjacent elements. The statement gives us three integers n, m, and k. A good array of size n is defined as each element is in the inclusive range from 1 to m. Okay, that's easy to understand. Next, that's it exactly k indices where okay certified conditions. Okay, that's mean two adjacent elements share the same value. Okay, so all we need to do is return the number of good arrays that can be formed. That's a combinatorics problem, obviously. Okay, since the answer is very okay, modulo, this okay is good. First, let brainstorming about these idea for this problem. But before dive into the problem, we need to take a look at the constraints here. You can see it's really large. Okay, 10 power, a million. Yeah, and m in case obviously from 0 to n minus 1. Okay. Okay. Let's think a little bit. Gonna write some example here, like for example this. Okay, for example, we got a array like this. Okay, you can see we got three elements here has the same value. Okay, three here has the same value too, and this and this and this. So these three obviously got 0 because it have not adjacencies. Okay, and about this group, we got one, two pair. Okay, two indices, the same as this with two. How about if we got one here too? So it's gonna be 3, right? So obviously is like continuous sub array that has the same values. A kind like C. So we got C minus 1 index I that I minus 1 equal to I, right? It's obviously you can understand that because we only care about the continuous elements that share the same values because as the statement give us here, it should satisfy this condition, so we only care about this. And how many index I we got? That is the length of that subarray minus 1, right? Because it obviously okay, you can understand what I say here. Because you can compare this to this and this. So this no, okay. How about the one element? For this is a subarray that had one continuous that had the same value, and we got like the length is 1, so we got 0. Yes, that's right. Got 0 index because there's no other elements to compare with the single value. So what we got here, that is so to let cause consider I C I C okay, I can C I Q continuous length of continuous subarray that has the same value, okay, and And assume that we got about p. We have p subarrays that okay, I mean the p subarray here is either the number of subarrays that's the continuous and have the same value. For example, in this we got this is one subarray, this is one subarray, this is one, two, this is one. We got 1, 2, 3, 4, 5. Got 5. P equal to 5. That is, we got 5 subarrays. That's continuously has that's samely continuously value. Continuously have the same value. Okay, continuously have the same value. Let's call it P. So we will got something like this. The k here. The case is the number of indices that is satisfied the conditions. It must be sum from maybe if from some that we index from 1, okay, from to p of ci minus 1. As I say before, we have c minus 1 here. As I say here, okay, you can see minus 1, and k is and out, and we need to find solution. That's find all the ways to form the array that match, not satisfy this new condition case. Okay, it's obvious. Let me write using math a symbol. Okay, sum I from 1 to p. P is a number of partition. I call it partition, mean we divide into many partitions, continuous partition. Okay, ci minus 1. Okay, a bracket to make it more clear. Okay, it must be equal to k given in the problem statement. Okay. Okay, and another thing we got a ci equal to n. Obviously, because p, we divided original array into p subarray, p continuous subarray. So ci, sum of ci must be, sum on ci must be equal to n. And here we found a relation between n and k here. With this, we got maybe we can write like this, p ci minus we got p, so it must be minus p, right, equal to k. So we convert this to, we move from the left side to the right side and change the sign. We got p, k plus p. Okay, and this is equal to n, so we gonna got something like, oh my god, something like n equal to k plus p. What does it mean? It means p equal to n minus k, which we already know about n and k because it's given in the statement. So we always need to find a way to divide into n minus k. So okay, let's take an example here when you use this array. Okay, let me change the color. Okay. For example, 1 to 5, we got like k is like 4, and m can be like 3, and n like maybe 7. We can do, and we can calculate the p is n minus k, that is 3, right? And I will draw something like this, 3, this, and gone left, maybe 3. That's it. We got this they have 2 indices, and this they have more 2 indices. We got 4. Okay. Another example, like I will reduce this using like 5, 5, 1. That's create 4 indices, right? And you know p equal to 3. I will prove this. We can so the remaining two elements must be another different value. So I gonna put 0 or 1 or 3 whatever. But you can see that we got 3 subarray 2. Okay, that's okay. Based on mathematics, we can prove the number of subarray we need to divide. Okay, got this. And now the problem turn to some interesting and familiar question we used to solve it before. It's combinatorics problem, and if you take a closely look at this problem, it may look like the earlier candy division problem. What does that mean? Yeah, okay. Back to the mathematical. Okay, you got this right. I will write this. Okay, sum of ci equal to n, right? We need to do this. And equal to e from 1 to p equal to n minus, you can see n minus b. Sorry. So, okay, this is equal to k plus b. Okay, k plus b, as I proved before, and okay, k plus b, and p is equal to n minus k, so we can write n minus k. This is n minus k. Just sorry. We convert from one side to another side, so it might be minus. Okay, let me write again to make sure you not see value. Sum ci minus 1 of e from 1 to p, as we can also write at n minus k, right, equal to k. Okay, so we can write like e1 from 1 to n minus k of ci minus n minus k equal to k. Equal to k. Okay, so this is equal to, you know, n, and sorry. I write again e from 1 to n minus k ci equal to, I convert k plus n minus k. Okay, and we remove this equal to n. So what we got here, we got a new problem, that's c1 plus c2 plus into c n minus k, right, equal to n. Okay, it's a candy division problem. That is distribute k candies among k people, where every person get at least 1 candies. Okay, and okay, the condition here is ci must be large and or equal to 1, right? Because if it's 0, it's not a subarray. Okay, that's right. So it turned to a candy division problem with n minus k children with total n candy. So okay, if you don't never heard about the Alec division candy problem before, I will explain it in short. Okay, like you got like n candy here, 1 2 3 4 5, you got 6 candy, and you need to divide it into distribute to your 3 child and 1 2 3 4 5 6 candy. So it's and each one must have at least one candy. So it's turned to the problem that you need to divide by cut the original array two times, like this. You cut it two times. That means you put two vertical like into the I the gap, yeah, the gaps between these values. So we got 1 2 3 4 5 gap, and absolute is n minus 1 gaps. Okay, and we need to choose two vertical lines in order to divide it into three subarray. That means we need to divide, for example, get maybe p, we need to divide to p child, p children, p children. So we need to use p minus 1 line. So on the possible ways, it choose the combinatory of p minus 1 of n minus 1 total n minus 1 total position to put p minus 1 vertical line into. So totally we got this. It's a basic combinatory theories. You can read more about it and do some deep research about the candy division problem. Okay, that's nice. We got the equation here. So this turned out we got the final. That means we got the number of way to divide the original array into some subarrays that is satisfy the conditions exactly k indices. That's the two continuous elements share the same value, and we got like n minus 1 and n minus k minus 1. Okay, here is the number of ways to divide, but it's just number of ways to divide, to distribute n candies among n minus k children. But actually we got an extra parameter that's the m, the values you can set to each element in the array. So it turns out more simple here. You got like you divide the array into something like this, right? Something like some continuously subarray stand next to each other. So the first element you can choose m on of this, on of the element inside a subarray. A partition must have the same value. So we got total m possible way to set that value for this subarray. Okay, and the next one, we must not, this value must be different from the previous, from the adjacent to adjacent, yeah, because if it had the same value as the previous subarray, it will be merged together. It will be merged together like this. Okay, that's why it's obviously this must be different value from each other. Adjacent only. So we only select the values that's different from the previous one. So we got n minus 1 possible way. Okay, for example, you choose this 3, so you must choose another one like 1, 2, or 4. You must exclude that previous value. How about this? The same. We only need to select the value that's different from the previous array and a previous subarray. We don't care about this because it's not adjacent. Yet it's not adjacency, so we got n minus 1, and the same as this is different from this, so you got n minus 1. That's it. So we got n minus 1 minus, and we got like p minus 1, yeah, remaining subarray, and this p equal to n minus k. Okay, n minus k. So our solutions. So finally the answer is c minus 1 n minus k minus 1 multiple by m minus 1 power n minus k minus 1. Okay, finally we got it. We got it. One line solution. But actually to build this in the code is a different thing. It's more difficult. Okay, let's test some water to start coding before starting coding. Okay, first of all we need to calculate this, right? The C, but you can see that the n is really large, really large. You can use a technique like dynamic programming to build the Pascal triangle. We need to find a O1 solution for this, or maybe On. That is to but you must that is use the original of C and K. That's it. This is n minus 1 factorial minus n minus 1 minus y k minus 0 and 2 sub n and 0. If you can see the nck formula, this is something like this. Okay, that's we need to calculate this. But actually, the thing we're gonna do is in the modulo. So we need to calculate the inverse. Yeah. Okay, modulo inverse. Yes, yes, you must find the inverse of a number. Okay, so I will implement the okay, I will implement the calculate the NCK first. The combinatorics. Combinatorics. Okay. I don't know. Yeah, combination. Okay, combination. Combinatorics is subject, right? Go. Void. Okay, now we need to. You know, calculate fact or init. Okay, just init the end. What gonna return here? Maybe fact, like maybe infer. Do I need to do this? Okay, maybe I will create a better publicly fact here and infer here. I'm gonna write init here with the n from 1 to n. Fact with style plus 1, but style and plus 1 2, while fact 0 is like 1. Fact y I minus 1 multiple by I modulo. That's obviously right. Obviously, to calculate the factorize factorial. Yes. Okay, to calculate it. Okay, the inverse modulo inverse. You can see Fermat's small theorem. Okay, you got something like this. A minus a power modulo minus 1 is equal to 1 in the modulo p. That's it, the theory. So we're gonna implement the power here. B. Okay, if b equal to 1 to return 0, if b 1 I return b. T by power a b divided by 2 half of b, and t double is case is even odd, so we must multiple more a y return t and p. Okay, path of n must be it must be power a and b the b minus 2. Y minus 2 here because minus 1 is equal to 1, so if minus 2 is equal to the inverse of this. Okay. So we need to calculate we can actually do this in on, the powers is on log n. or log n, but there's a way to calculate the inverse of every factory. I mean inverse every factory using this formula. If you're interested, do some research about it later. The keyword is factorial inverse in ON. Okay, that's one. You might not understand this if you don't familiar with this. Okay, got it. So just in it. Let's take a look at the maximum value is n. Okay, it must be n. When it's n, gonna okay. We need to write the function of calculate c k n here. C c n k here. It must return something like fact of n multiplied by inverse of k with minus k modulo. Okay, got it. But if it's less than 0, so just return maybe 0, maybe something like that. Okay. Okay, let's take a test first. Okay. The formula here, the answer is c of m-1 minus k minus 1 multiplied by m multiplied by power of m minus 1. The base is m minus 1 and the power is m minus k minus 1 module. Remember to cast it. It do something like this. Never forget to cast it because it may be overflowing. Got it. I hope it. AB. Oh, what is B? Oh, in fact, N, and we got mod. Okay, just take a look at 10.4. Oh, it's wrong. You can see it's wrong. So maybe some bug here. That and okay. Continue. There's my mistake here. It must return A. It's a silly mistake. Okay. If it's returned something like 0, it's wrong. Okay. Wait a minute. Make the test here is the mode in the and there's something wrong. 0. Okay, 0 is correct. Okay, it's in the inverse array is correct. So how about 10 power 4 is to return 0? What does it mean? Oh, it must be 1. I know. Okay, it's right. So I'm gonna do some debug here and okay. Okay. Check it out. What is wrong? This might be return something like 0. Right? Zero. File. Okay. Minus K is. Okay, the inverse array was wrong. Okay, the wrong here is from the inverse. Okay, let me calculate this again. 0. It's right. It's right. It's not be right. Yeah, okay. This one. Oh, on 0. Why? What makes you become on 0? Fat. See fat at e plus pass and fat of 0 is what? 1. Why the powers? The power here. Equal to 0 return 1. Yes, that's right. But if 1, so we're gonna return something like 8. That's right too. Okay. So it's okay. So the wrong is from this function, right? It's a return 0. Okay. Oh, it's looking so correct. But actually it's returned something wrong. Just do a little test here. Sick equal to. Yes, that's right. But why? What is written 0? Mode. Why? Why is written 0? Why? I can't believe it's written 0. Take a look at this. -2. That's right. That's what I do, man. And what's the n? N is 10. Okay, 10. So gonna just wait a minute. I'm nearly reached it. I'm nearly reached. Just do not happen. Inverse. What can it? Oh, you can see it's overflow. What? It just returned past, as you can see. Huh? What happened to you? Okay, never mind. It's like applying non-zero offsets to null pointer. What do you mean? What do you mean by null pointer? I just okay, I just forgot to initialize. Too many mistakes for a night. You know, I have something more thing to do tonight. It's way too much time fixing some silly bug. Well, I thought that my solution is pretty fast, but actually it just lying here. hmm So like, can we optimize more? hmm I don't just see the first one solution. Okay, you can see it's really the same as me. Okay, but they use the impairments of powers. This more faster. Maybe that, and they use long to prevent the casting, so it's made faster. But the overall our solution is here.